So hi everyone, today we are going to introduce the paper Latent Consistency Models. The title is Synthesizing High-Resolution Images with Few-Step Inference. So the main author is from Tsinghua University, and also is Simian. So my name is Zhao Shu. My partner's name is Bo Xiao. We are going to present this paper. So the outlines of this presentation divided into 6 parts. First, I will give brief introduction to the diffusion model like DDPM or stable diffusion, and introduction to consistency models. We call it CM. And also, then I will introduce the latent consistency model, which is our today's topic, LCM. Then I will compare CM and LCM. And last, my partner Xiao will give us an evaluation and conclusions of it. So let's first look at what is diffusion model. So the idea is that we convert noise from some simple distribution to a data sample. So in simple words, we can describe diffusion model as two processes. One process is the forward process, which is adding noise to a clean image, gradually adding noise to a clean image. So we predefined some scheduler like the beta down here. So we have beta 1, beta 2 to beta t, and they all are in the range of 0 to 1, and beta 1 is less than beta 2, and so on and so forth. And also we define the Q, which is the noise step. Given xt minus 1, we need to get the xt. So that's a normal distribution, normal Gaussian distribution. So when beta is getting larger, the picture is more like a noise picture. It's getting noisier. That's the forward process. And then we can see up in the graph, we have p theta. So we given xt, we need to get xt minus 1. So that's the reverse process. Because in the math, we cannot directly just remove the noise from a noise picture. So here, and authors, the authors wants to use a neural network to represent the probability distribution of the backward process. So that basically use a neural network to predict the noise that was added to the picture at these time steps. Yes, so we define p theta. We need to predict xt minus 1 given xt as a normal distribution, and we have two parameters, the mu theta xt at time step t and the sigma theta xt at time step t. Sigma is the variance. So actually we need to predict the mean of it, but previously, as I said, we are converting noise from it. And so that the reason is in this the second paper. You can check out this paper. The paper said we can use the predicted noise to get the mean of it by some conversions. So in this way, we don't need to use neural network to get the mean of it, which is very hard for a neural network and time consuming. So instead, we can predict the noise of it by using these equations to reconstruct the mean. So that's the second line here. So after that, we have the model parameterization. So we need to define what's the loss of this model. So we actually calculate the KL divergence. I also posted the link here was the KL divergence. So we need to calculate the KL divergence between two Gaussian distribution, which I just used the red arrow point here. So I just said before, P theta is the neural network predicted noise, and the Q is our manually added noise. So we want to minimize the difference between predicted noise and the we added noise. That's called LT. So we sum them up. We have our loss LT plus L1, L0, and so on and so forth. So in DDPM, and that's the standard diffusion model, we have 1k steps. That means t equals 1k. So finally, we can define our loss at time step t equals the noise noise minus the neural network predicted noise. The E theta xt given time step t is the predicted noise, and the E is our manually added noise. So we calculate the MSE, the square root, the squared error. So we formally define this loss. So after that, according to the consistent model, this paper, the author described that all kinds of diffusion model is actually a process of diffusing data with stochastic differential equation (SDE). So this is actually same as before. This whole process can be seen as this SDE. The SDE is actually the forward process. We have a mu, we have a sigma, and we have time a little time step dt, and another wt, which is a standard Brownian motion. So the author described the forward process is actually an SDE. So in here we have wt. So the Brownian motion in high level actually contains 3 points. The first one, it starts at 0. The second one, it's described that the increments or the decrements between time intervals actually independent. So let me give you an example. For example, we have time 3 time steps. One is time 0, time 1, and time 2. It may be time 0 is the time at 0, and time 1 is like 10 seconds later, and time 2 is like another 10 seconds later. So at the first 10 seconds, the increment and decrement is independent from the second 10 seconds. But they need to have a constraint that the end point of the first 10 seconds is the start point of the second 10 seconds. So we can think of curved line. They are continuous. There's no jump points. That's the second one. The third one is the expected value of the process at any future time is equal to the current value. So that's what standard Brownian motion it is. You can also check online for it. Okay, with that information, the author also said that the reverse process is actually can be seen as the solution trajectory here. The dxt equals to the mu xt minus 1/2 the half of sigma t squared and the derivative of log ptxt. So the author mentioned that the derivative of log ptxt is the score function of ptx. So we can use actually the score matching method to estimate the derivative of log ptx. So in this way, so we can actually compute it. We can construct the model of this function, and from this graph we see that we can actually draw the lines of it, and so I will later talk about why we need to use this. So from this graph we can easily to see the whole process. So we start from the left. We have a clean image x0, that's data, and then we describe the forward SDE, that's the forward process gradually adding noise, because each time we add a Gaussian noise which is unpredictable, even though it's the Gaussian noise, the shape, the line looks the same, but each time it's different. So you can see the zigzag lines here. And a good property of the SDE is that it can be, every SDE is duped with probability flow ODE. So the ODE is get from the score matching here. We can replace the derivative of log PTX with the score matching function S to plug this S into the equations above. Then we can get the probability flow ODE. Then after some time steps, we got the XT, which we called the prior, and it's also the noise picture, the pure noise. And also we go and that after that we can go through the reverse process to denoise the picture by certain iterations. That's what we call the reverse SDE. Also, by using the score matching method to create this model, we can reverse the SDE and the ODE by estimating the score of it, so to get the clean data. So in this way we can construct the graph here. Okay, so that's why the author from consistent model, they say every diffusion models can be seen as a score-based generative model. This is a new type of generative model like Jian or like VAE. So that's diffusion models. So let me talk about latent diffusion model. So the only difference is actually the red part, the pixel space. So given a clean image X, it will go through an encoder, and we will get a Z. Z is the latent vector. So this process is actually extract the important features from the clean image X, and using this abstract vector to do the whole process of the diffusion process and the denoising process. And after that, we will go through a decoder to get back to a clean image. The clean image may not same as the input image, but they are similar. And you see also we have a conditioning, some text or some other images to guide our denoising steps to make the image more like what we want. I will talk about this later. Okay, that's the whole process of latent diffusion model. The only difference is the red part. Just remember this point. Okay. So after that, we need to talk about what's the consistent model. From this graph, you can think the blue part is actually it's the same process of a diffusion model. So we have a probability flow ODE, that's the forward process, and then we have another reversed SDE, that's also the blue part downstairs or down here. Okay, so what the consistent model is just used. So the idea is to map any point in the reverse process to the original point x0. So we need to train this model to map any point to the original point. So in the paper, there are actually two ways of training this f theta. One is the consistent distillation. So we use the pre-trained the diffusion model to get f theta. Another one is trained from scratch, but that's not our topic today. So we will focus on the consistent distillation this time. Okay. So in order to call it a consistent model, we have to satisfy with these 4 points. The first one is the consistency property. So given t and t prime, in between the e and t, e is the Gaussian noise, t is another Gaussian noise after t time steps. So first we need to make sure every output from these time steps, we need to get the same outputs, same clean image. That's the idea. Secondly, we need to parameterize this model as f theta xt equals the c skip t x plus clt f theta. F theta is a neural network. Usually we use UNet for it. So for example, if t equals Gaussian noise e, then f theta xe equals 1 times x plus 0 times f theta. So that means if we just add one Gaussian noise to this clean image, we should get back to the clean image by using f theta, this consistent model. After that, we need to construct the loss function. The loss function is L theta minus and phi equals to the expectation of a difference function. D is a difference function to tell the difference from two outputs, f theta and f theta phi, f theta negative. So at first, at time step tn plus 1, we get an output. Output is a clean image from this consistent model, and then we use one-step estimation, number 4, to use some ODE solver and the input of xtn plus 1 to get xtn. So after we have xtn, we run the consistent model to f theta minus to get another clean image. Then we tell the difference. Then that's our loss for the train. So theta phi is actually what we want, the target network, and the theta is the teacher network, because we are distillation from a teacher model. We usually use stable diffusion model for it. So after this, we need to talk about our today's topic, latent consistency model. So the latent means that we compress the high dimensional image data into low dimensional latent vector z, like I just mentioned before. We add this red part to the consistent model, and that's the main point of latent consistent model. That's the first thing. So the difference between consistent model and LCM, you can see from the model parameterizations. We can see we use ZCT as our input, as our parameters. So we replace X with T. We replace X with Z. And then we have some text C. The actually consistent model also can add C into it. That's just some text to guide our denoising steps. So the main difference is we replace X to Z. Accordingly, we need to change our loss function. Also, we need to change X Tn plus 1 here to ZTN plus 1. Also the XTN to ZTN. So the another difference is that they integrate class-free guidance into the latent consistent model. So originally we have E theta, this is our model, ZT, C, and T. But right now we have another variable, W. W is the guidance scale. So which means if we increase the guidance scale, the model predicted image will more like the the description of the text. So for example, if we put some text, say like I want a man fly in the air, so the resulting image were more like a man flying in the air, not a woman flying in the air. So basically it will increase the image quality. That's the idea of class-free guidance. Okay, and also we notice that there's a minus here, and inside the minus w e theta we have a known symbol here. That means we do not give any hint, give any text to this denoting step. So we want to move away from the no guidance and outputs and move towards to our guidance direction. So accordingly, we have to change our loss function to include w inside it, and w and n are uniformly sampled from interval w main, w max, and 1 to n plus 1, n minus 1 respectively. So another important point about LCM and is the skip time steps. So instead of ensuring consistency between adjacent time step and Tn plus 1 to Tn, LCM aims to ensure consistency between the current time step and the k steps away. The reason behind it is that they also find out in the latent space, the output between adjacent time steps are similar. So we actually do not need to distillate the model one by one time step by one time step. Actually, we can skip some time steps, skip some iterations from the train, for the training steps, for the training purpose. So and by some empirical study, they found out k equals 20 is the best. So with this knowledge, we can redefine our loss function to replace z. Originally we have ztn plus 1 and ztn, but right now we use ztn plus k and ztn. So that means our output an image from time step n plus k, and then we use one-time solver, ODE solver, to produce ztn and use our consistent model to predict another clean image and compare difference. You can see the jump here. In this way, we will greatly reduce our computations. That's very important. And also, we can accelerate the convergence time. So combine this all, we have our algorithm. This algorithm is completely based on consistent distillation from consistent model, the CM1. The only difference is the blue part. So in the blue part, we have our ODE solver. We have a noise scheduler, alpha, theta, sigma, and guidance scale, a skip interval, and encoder and decoder. In the loops, the main change is the z, the one step estimator z. ztn is get from ztn plus k with our guidance scale w and our ODE solver phi. That's the main change, and also accordingly we need to change our loss function to include the guidance scale and the skip connection. At last, we use the same stochastic gradient descent in consistent model to train our latent consistent model. Also, that's the whole idea of LCM. And then last, my partner Potential will introduce the evaluations of this model and the conclusions. Thank you.
Evaluation part. For the data set, they choose two subsets from the Lion 5B, the Lion Athletics 6 Plus and the Lion Athletics 6.5 Plus. The experiments consider resolution of 512 times 512, and the other resolution is 768 times 768. For the 512 resolution, they use the Lion Athletics 6 Plus, which comprises 12 million text image pairs with predicted aesthetic scores higher than 6. For the 768 resolution, they use the Lion Aesthetics 6.5 Plus with 650k text image pairs with the aesthetic score higher than the 6.5. For the model configuration, for 512 resolution, they use the pre-trained stable diffusion v2.1 based as their teacher model. For the 768 resolution, they use the pre-trained stable diffusion v2.1. They train the LCM with 100k iterations and use a batch size of 72 for the 512 resolution setting and 16 for the 768 resolution setting. They set the learning rate equals to 8 times 10 to the power of minus 6 and set the EMA rate equals to 0.99943. For the augmenting PFODE solver, and the skipping step k in the equation 17, they use the DDIM solver with skipping step k equals to 20 and set the guidance scale range from 2 to 14. And for the baselines and the evaluation, they use 4 different solvers, including the DDIM, DPN, DPN++, and the guided distill as the baselines. For the first 3 solvers, DDIM, DPN, and DPN++ require more peak memory per step with classifier-free guidance. And the guided distill requires, which is the closed source model, it requires 2 stages of guided distillation. The authors strictly follow the training procedure outlined in the paper to reproduce the results. And in the original paper, they used a large batch size of like 512, which requires at least 32 100 GPUs. That's the reason why they reduced the batch size to 72 for the same 100k iterations. LCM achieves faster convergency and superior results under the same computation cost. Generate 30 case images from 10k prompts in the test case, which means 3 images per prompt, and adopt the FID and CLIP scores to evaluate the diversity and the quality of the generated images. They use the VITG14 for evaluating the CLIP scores. Here's the results. The quantitative results in the table 1 and table 2 show that LCM outperforms the baseline method at both resolutions, especially in the low step regime, which means 1 to 4, highlighting its efficiency and superior performance. Unlike the DDIM, DPN, and DPN++, which require more peak memory per sampling step with CFG, LCM requires only 1 forward pass per sampling step, saving both time and memory. Moreover, in contrast to the 2-stage distillation procedure employed in the guided distill, LCM only needs 1-stage guided distillation, which is much simpler and more practical. For the ODE solvers and the skipping step schedule, they compare various solvers for including the DDIM, DPN, DPN++ for solving the augmenting PFODE. From the figure, we can know that Using the skipping step technique, LCM achieves faster convergence within 2K iterations in 4-step inference stacking. Especially the DDIM solver converges slowly at skipping step k equals to 1. While stacking k equals to 5, 10, 20 leads to much faster convergence, underscoring the effectiveness of the skipping step method. Also, the DPN and the DPN++ solvers perform better at a large skipping step, let's say k equal to 50, compared to the DDIM solver, and which suffers from the increased ODE approximation error with large k value. Also, very small k value like 1 or 5 result in slow convergence, and very large ones like 50 for DDIM may lead to inferior results. The next is the effect of the guidance scale omega. They also examine the effect of using different CFG scalars omega in LCM. Omega balances sample quality and the diversity. A large omega generally tends to improve the sample quality indicated by the CLIP scores, but may compromise the diversity measured by the FID scores. Beyond a certain threshold, an increase omega yields better CLIP scores at the expense of FID. Figure 4 presents the result of various omega across different inference steps. We can see from the figure, using large omega enhances sample quality, which can be seen by the CLIP scores, but result in relatively inferior FID scores. The performance gap across 2, 4, and 8 inference steps are negligible, and highlighting LCM's efficacy in like 2 to 8 step regions. They present the visualizations for different omega in figure 5. One can see clearly that a larger omega enhances sample quality, verifying the effectiveness of their one-stage guided distillation method. Next part is the downstream consistency fine-tuning result. And they use Pokemon dataset and the Simpson dataset to evaluate the latent consistency fine-tuning. The dataset can be divided into 2 parts. The first part is 90% of the dataset is used for the fine-tuning, and the rest 10% for testing. They utilize the pre-trained LCM that was originally trained at the resolution of 768 times 768 resolutions, and they fine-tuned the pre-trained LCM for 30K iterations with a learning rate 8 times to 10 with the power of -6. The figure shows that the fine-tuned LCM is capable for generating images with customized style in few steps, showing the effectiveness of the proposed method. The last section is the conclusion. In this paper, the authors introduce the latent consistency model, which is a highly efficient one-stage guided distillation method that enables few-step or even one-step inference on the pre-trained LDMs. The authors also propose the latent consistency fine-tuning, which can be used to enable few-step inference of LCMs on customized image datasets. The extensive experiments demonstrate the superior performance and efficiency of LCMs. For the future study, the authors are trying to extend the method to more image generation tasks, such as the text-guided image editing in painting, and the super resolutions. That's all for our presentation. Thank you.